Here you are asked to determine the force that a 90 kg man exerts on the floor of an elevator when it is at rest. Okay, so one strategy, right, when solving questions on dynamics is to draw a diagram. So let's consider the lift, and then you have a man in the lift. So the question is looking for the force that the man exerts on the floor of an elevator. Okay, so for this one, we can have two free body diagram. One is the man, the other is the elevator. So let's do this. Consider the man. Okay, there will be a force downward which is due to the weight of the man. Okay, so we know that our weight W equals to mg. The mass is 90 kg. So I will just put 90 g, where g is 9.81. So the weight of the man is 90 g. Okay, the man is in contact with the floor of the elevator. So there will be a contact force. So there will be a normal reaction force. Okay, the normal reaction force add on the two legs. But we will just draw a resultant normal reaction force, okay, on the man through the center CG of the man. Okay, so this is the normal reaction force. And I'm going to call it N. Okay, so N is the normal reaction force. So N is the force exerts by floor of the elevator on man. So this will be the two forces acting on the man. Okay, if you were to draw the free body diagram for the elevator, okay, let's take a look. I will have the weight of the elevator, which I do not know. Okay, so I'm going to call this weight of elevator. Okay, there must be something that is pulling the elevator. So probably there is a force upward, which again I do not know. So that I'm going to call that pulling force on elevator. Okay. Then because the man is in the elevator, so the man will exert a downward force. And according to Newton's third law, this force must be numerically same as N, but in the opposite direction. So if I were to take a look at these two free body diagram, to solve for N, I will definitely have to use the free body diagram for the man, because I know the weight of the man, but I do not know the weight of the elevator and the pulling force on the elevator. So let's consider free body diagram for the man. Okay, so there are two forces acting on the man, namely N and 90G. So when the elevator is at rest, the man is also at rest. So if it's at rest, it implies not moving. If it's not moving, according to Newton's first law, the resultant force should be 0. Okay, so if I were to find the resultant force on the man, okay, you find that there are two forces. Okay, randomly you can take upward as positive. It doesn't matter. So N minus mg, and this will be equals to 0. And therefore, my normal reaction force will be equals to the weight of the man. In this case, it's 90G. Okay, so value for G is 9.81. So the if you press your calculator, okay, the value is 883 Newton. Okay, let's move on to part B. Again, you're finding the N, which is the force on the floor of an elevator that the man exerts. So by Newton's third law, we know that this force is the same as the force that the floor exerts on the man. Okay, so it's finding N. So when it's moving at a constant speed of 1.5 meter per second, when the speed is constant, this implies that the acceleration is 0. Okay, because there is no change in the speed, therefore acceleration is 0. And then from here, we know that the F net is 0, because F net is ma, and this is 0. So it's same as part A, where the resultant force is 0. And the answer here is also 883 Newton. Okay, let's move on to C. Again, C is at constant speed, which is similar to part B. Okay, just that it's coming down. But whether it's going up or coming down, as long as the speed is constant, the acceleration is 0. If the acceleration is 0, the net force again will be 0. If the net force is 0, then the N will be 883 Newton. Okay, let's move on to part 4. Part 4 say rises at a constant acceleration of 1.5 meter per second squared. So now there is an acceleration. Resultant force is no longer 0. Again, if I were to use Newton's second law, F net equals to ma, the resultant force, in this case, if I consider the man, remember we have the free body diagram for the man, so let's just consider the man. The net force will be equals to 90 times 9.81. Okay. Then if I were to look at the forces acting on the man, you're told that it's going up. Going up, that means the outward force have to be larger. So I will take my outward force on the man, which is M. That means N minus mg must give me the resultant force. So this F net is also equals to N minus 90g. And if I were to call this equation 1, call this equation 2, these two are equal. Okay, because both are talking about the resultant force on the man. So I will have 90 times 1.5 equals to N minus 90 times 9.81. So from here, my N will be equals to 90 times 1.5 plus 90 times 9.81. Okay, if you press a calculator, you end up with 1020 Newton. In part E, you're told that the lift is going down. Okay, so now downward force should be larger. There's an acceleration of 1.5 meter per second squared. So like part D, we will have F net. The net force now is 90 times 1.5, because the acceleration is 1.5. So yeah, I should write the equation first. So F net is equals to MA. M is 90. Acceleration is 1.5, but it's going downwards. Okay, so I need not put a negative sign here. I just need to know that, I just need to indicate that it's going downward. That is good enough. So the resultant force is downward. So in this case, if I were to look at the free body diagram for the man again, the downward force have to be larger because it's accelerating downwards. So my equation for net force will be 90 minus N. Okay, so the F net here can also be obtained by 90 minus N. So same like before, I have equation 1 and equation 2. So I equate both of them. Equation 1 is the same as 2. Both are the resultant force on the man. So 90 times 1.5 will be equals to 90 G, right? I've forgotten the G. 90 times 9.81 minus N. Therefore, N will be 90 times 9.81. We'll bring this over. 90 times 1.5. So the resultant force here is 748 Newton. Okay, so when the man is going down a lift and the lift is accelerating, you find that the force that the man exerts on the floor is actually smaller compared to when it's going up.